We brought in some local talent for the next talk. I'm Richard Samworth, who's going to be speaking on isotonic regression in general dimensions.
Thank you, Richard. So it's a great pleasure to be here, having travelled so far. I'm going to be speaking about some recent work on isotonic regression, so I think this might complement Bodhi's talk quite nicely. It's joint work with three fantastic collaborators. One is Roy Han. He's a PhD student at University of Washington working with John Wellner. He's finishing his PhD this summer and he is going to Rutgers next year. Then there's Tengyao, who just left, but he is my postdoc here and will be joining UCL next year. And then Sabyasachi Chatterjee, who was at Chicago for most of the time we were working on this project, but has now moved to the University of Illinois at Urbana-Champaign. Okay, so yeah, Bodhi set this up quite well, quite nicely for me in many ways. But let me just recap that isotonic regression is perhaps the simplest and most widely studied problem in shape-constrained estimation. I don't think we need to think too hard to come up with examples of settings where it's reasonable to think of the behavior, the dependence of a response on covariates as being monotone. If you think about educational studies and you want to think about the dependence of kind of GPA on high school rankings or standardized test scores, then you might easily imagine that would be monotone. To give a multivariate example, a lot of work's been done on genetic heritability studies where it's often reasonable to think that phenotypes like height or fitness or disease might depend in a monotone way on genetic effects. So a lot of work has been done to try to simplify the class of functions because you're sort of worried that you've got d covariates, you're going to have a cursive dimensionality. So people have looked at additive models and also other simplifying structures like models based on minima or logarithms or products, but actually those have been found to be pretty unsatisfactory. So for this talk, we're actually going to revert to the kind of more general problem and just think about isotonic regression over a class of block increasing functions. Unfortunately, that definition hasn't changed since Bodhi's talk a moment ago. So we recall that we have a natural partial ordering on R to the D where we say that x is less than or equal to x prime if every coordinate is x is less than or equal to the corresponding coordinate of x prime. And then we can talk about the class of block increasing functions which just respect this natural partial ordering. Okay, so our setting is going to be rather straightforward. We have independent observations. I'll have a generic point x and y, but my training data, as it were, is x1, y1 up to xn, yn. And they satisfy a standard regression model where we have our regression function f0 is a measurable function. It may or may not be itself monotone. Okay, so we'll look at both settings here. We've got standard normal errors, and I also want to allow my covariates either to be fixed or to be random design points. It turns out that the fixed design point case is much easier to study mathematically, although the results turn out to be pretty similar in the two different cases. And we are going to look at the most obvious estimator in this setting, which is the least squares estimator. So we're just looking to minimize the residual sum of squares over all block increasing functions. Notice that this estimator here is only well defined at the covariates that I observe. Okay? There are several different ways I might extend its definition to the whole of 0, 1 to the d. It turns out not to matter how you choose to do this, but we only have this well defined at the covariates initially. And we're going to study its performance at least in the fixed design setting in terms of its empirical risk. When we're dealing with random design covariates, it makes sense also to think about what the risk would be, what's the expected squared error at a new observation. Okay, so we'll consider both of those risk functions. But in the fixed design setting, we're only going to be interested in this loss at the observations. Okay, and there are going to be two settings that I'm going to be particularly interested in. One is the fixed lattice design, where you're that define a DAG that looks like this, and then the other is a random design setting which defines a DAG that looks like this, where all the arrows are pointing up and to the right. Okay. And we just need to remember that the vectors that respect the partial ordering lie in what I'll call the monotone cone of G. So this is an intersection of some half spaces. Okay, so that's a set that's closed under multiplication by a non-negative scalar, and so it's a cone, and it's an intersection of several different half spaces. So in terms of computation, if you want to think about the problem of trying to compute an estimator that's defined as the least squares projection onto a convex cone, probably the first thing you'd think about doing, or at least in this case where your convex cone is an intersection of half spaces, is to do iterative projection onto the different half spaces. But it turns out this is called von Neumann's algorithm, but it doesn't actually necessarily converge to what you want to. So for instance, let's say this is one half space and this is another half space, so I want to project onto this intersection here. So if I draw the polar cone like this, and let's say I've got a point here, okay? I want to project this onto the intersection of these half spaces. If I use von Neumann's algorithm, then I'm going to project onto here, and then I project onto here, but that's not equal to where it should have been, which is here. Okay? So von Neumann's algorithm doesn't necessarily work. There are two alternatives. One is to modify von Neumann's algorithm using Dijkstra's algorithm, and the other is to use interior point methods. Let me just illustrate what Dijkstra's algorithm does. So this is a slightly more general setting where I'm projecting onto the intersection of two closed convex sets. So I've got this initial point x0, and the intersection of these two sets is this shaded region up here. So I first of all proceed, as you would imagine with von Neumann's algorithm, I project onto one of the sets, then I project onto the other set, but I have to allow myself some memory in this algorithm. So I allow I traverse back in the direction of the original projection, and then project that point back onto the first set again. Okay? And I can play the same game where I remember that this was my second projection, so I go back in this direction before projecting this point onto the new, onto the second convex set. And I can play the same game. And actually you can prove that this algorithm does indeed converge, so that if I kept running this, then this point would be projected onto something about there.
Why do you have to go back?
Exactly to avoid this problem I mentioned, I described on the board, where you get stuck at the wrong place.
If you just keep projecting from one.
In general, I think this example illustrates that you don't get to the right point in this example, right?
How far do you have to go back?
The same distance as you moved in the step two before, in the case of two half spaces, right? Okay, so there's been a lot of work done on isotonic regression. It's got a long history. Almost all of it concerns the one-dimensional covariate case, and in that case, the problem's more than 60 years old now. Some work by Brunk in 1955, but it's still a very popular topic. And so in particular, there's been a lot of work in recent years that's gone after adaptivity results. And I'll say more about those later on. Very recently, last year, there was a paper that was looking at the bivariate problem in a fixed lattice design case. So in some ways, our work builds on that work. But didn't treat the random design setting. But I should also mention there's been a lot of work on these sort of various different simplifying structures you might be willing to assume, in particular where you might have additive models. So N.O. Mammam has a paper from 10 years ago, 11 years ago now on that, and I worked on that recently too. Okay, so let's first of all think about the fixed lattice design case. So here is the lattice that I'm imagining. For simplicity, I'm just going to think of my sample size as being a dth power of a natural number. So that natural number will be n1. So n1 is n to the power 1 over d. And my set of design points then is this lattice, which I'll write with a blackboard bold L, dn here. And of course it looks like that picture there. So because my risk only looks at what happens at the observations, it makes sense to define a vector in Rn, the theta 0, which is the true signal vector at the observed covariates, and then my estimator is just I can think of that as a vector 2 in Rn, that I just collect together the least squares estimator at the design points. And now I can write my risk function as a function of the vectors theta hat n and theta 0 instead of as a function of f hat n and f0. Okay, I want to study the behavior, the risk of the least squares estimator, and that's, remember, the projection of this response vector onto this monotone cone. And there's a very beautiful result due to Sabyasachi Chatterjee from 4 years ago now that characterizes this least squares projection. So I should mention that there are two S. Chatterjees associated with this work. There's my co-author Sabyasachi Chatterjee at UIUC, and then there's Prof. Chatterjee at Stanford. As far as I know, they're not related. This is Prof. Chatterjee's result. Okay, so it says that if I've got a point mu in a closed convex set K and I've got an error vector epsilon, the aim of this result is to characterize the risk of the least squares projection onto this closed convex set K. Okay, so here is my mu, my true signal, and I observe mu plus epsilon, the corrupted version of it. My estimator is the least squares projection of this observation onto the closed convex set. Okay, and I want to characterize this distance here, the squared estimation error. Okay, and the bounds are very interesting because essentially they match the upper and lower bounds, and it's saying that this squared risk is like t0 squared, where t0 is defined here. Okay, up to some small error, because I'm thinking of t0 as being greater than or equal to 1. Okay. This t0 is maybe a little bit difficult to get your head around initially, but it's not too bad. So let's think of my point mu as being in the interior here, and so at least for small t, you can see that this radius, this expectation is going to increase linearly with the radius t. Okay, at least for small enough t that I'm still within my closed convex set. But then for large t, this half t squared term is going to win. Okay, that's going to dominate. So at most, this term can increase linearly in t, but eventually this half t squared is going to win. And in fact, what you can show is that this function increases from 0, as you would expect, and goes to minus infinity in the tails, but it's actually a strictly concave function. Okay. So in other words, this t0, this maximum is going to be well defined.
Sorry, Richard, what is the space M of LD?
That is the set of monotone vectors on the lattice, respecting the ordering of the lattice. So I'd like to try to identify this point t0, this maximum. That turns out to be rather too difficult for me. But what I can do instead is try to find an upper bound for the point where we cross this t-axis again. Okay? And certainly if I find an upper point bound for that, then that's t star is going to be an upper bound on t0, and t0 is, or t0 squared is the squared risk that I'm after. Okay? Okay, so to summarize then, I can bound my risk by t star over n for any t star satisfying this this inequality here. Okay? So, okay, now I want to see if I can do a calculation where we get some insight into what's going on with the left-hand side here. So, I'm going to try and find an upper bound for the left-hand side here, and then find a t star that satisfies this inequality when I've replaced this left-hand side with an upper bound. Okay? And that'll do for the t star that I'm after. So, okay, what do I got to deal with? Expected supremum over theta in the monotone cone. Okay, so I'm going to fix my theta 0 to belong to the monotone cone, so it's a well-specified case, and to have infinity norm at most 1. Okay? This blackboards are rather too small here. I'm not going to be able to write too much, but I'll see how I do. Okay, so this is the quantity I want to study. And what I'm going to do is subtract and add something into this expression here. And the expression I'm going to add is theta 0 bar, which is just going to be the average value of the true signal. Okay? So, if I write this as epsilon minus epsilon comma theta minus theta 0 bar 1n plus epsilon theta 0 1n minus theta 0. Okay? Then what I notice is that this second term doesn't depend upon theta, that I'm taking the supremum over, and in fact it's just taking the expectation of the inner product of epsilon with a fixed vector. Okay, but epsilon is a mean zero quantity, so this guy is going to vanish. Okay? And now what I'm going to do is I'm going to enlarge this set that I'm taking the supremum over, and therefore I'm going to only increase this quantity. So my claim is that if theta minus theta 0 is less than or equal to t star, and the L infinity norm of theta 0 is bounded above by 1, these are vectors in Rn, then the Euclidean distance of theta from this average can't be bigger than t star plus n to the 1/2. Okay, it's just a triangle inequality. And then I've got the same quantity here. And now I just have to realize that subtracting a constant vector doesn't change whether I'm monotone or not. I'm still within the monotone cone, right? So I can just relabel this guy so this is the Euclidean ball of radius t star plus n to the 1/2. and then just epsilon comma theta. Okay? And now I can say the same thing again, that this is just linear in this radius. This supremum just increases linearly in the radius, expected supremum does. So that comes out as a constant. And I get t star plus n to the 1/2 times the expected supremum over theta belonging to the monotone cone intersect the unit ball of epsilon theta. Okay? And then just one more bound that's convenient rather than necessary. I'm going to bound this by the square root of a quantity that I'll call delta of this lattice, and this is called the statistical dimension of this monotone cone. So delta is the expected value of the supremum of epsilon theta squared. Okay, so it's closely related to the Gaussian width, but I'm just taking a square and then a square root outside, so that now I've got things sort of how I want them, because the dependence on t star is very simple, and it just involves this property of the monotone cone, its statistical dimension. So statistical dimension is a generalization to sort of more general convex sets of the notion of dimension of an affine space. Okay. In fact, so now what I've got to do is I've got to solve the equation that bounds this guy here by t star squared over 2, right? And if I do that, I see that it suffices to choose t star to be the square root of this statistical dimension plus something a little bit complicated but not too awful. Okay, so that might not be so readable, but all it is, it just involves, all I need to know to know t star is something about the statistical dimension of this monotone cone. Okay? Okay, so I've reduced the problem to computing the statistical dimension. So this is a very interesting problem. In one dimension, there's a very beautiful paper that I highly recommend by Amalungsen et al. From 2014 called Living on the Edge. I forget exactly what the second half of the title is. But it introduces this idea of statistical dimension and all sorts of characterizations and properties of statistical dimension. It also computes exactly what the statistical dimension of the monotone cone is in one dimension. So, in fact, if we have an upper bound and a lower bound, when d is 1, the exact expression, so the matching, this is nothing asymptotic, the exact expression is the sum of the first n terms of the harmonic series, so basically log n, okay? When d is 2, this recent paper by Chatterjee, Gunterbuiner and Sen gets a bound of log to the power 8n, okay? So it's again logarithmic in n here. And by the end of the talk, I want to try and fill in the rest of this table, where we're going to have a d greater than or equal to 3 here as well. Okay? And the argument for how we're going to compute this statistical dimension is surprisingly simple, and you think it's too crude to be good, but it turns out to be sharp up to poly-logarithmic factors. So let me illustrate it pictorially. Let's suppose I want to compute the statistical dimension of this lattice here. Okay? And the way I'm going to do this is to say, well, if I remove constraints from this lattice, then I increase the statistical dimension. Okay, I increase the cone and therefore I increase the statistical dimension. And so what I'm going to do is I'm going to delete all the edges that go in the vertical direction. So we're just going to get these ones that look like this. Okay? So I've deleted edges, I've increased the size of the cone, and therefore I've increased the size of the expected supremum that I need to have in the calculation. But now I've just got n1 copies, or n to the 1 over d copies, of a d minus 1 dimensional lattice. Okay? So I can proceed by induction and say that the statistical dimension of the monotone cone in d dimensions is bounded above by, well, where does this n to the 1 over d come from? This is just then a Cartesian product of these different lattices, and one of the nice properties of statistical dimension is it adds over Cartesian products. So I just have n to the 1 over d times what I have in d minus 1 dimensions. And I can keep playing this game. Interestingly, I'm not going to go down to 1 dimension. I'm going to truncate this induction when d is 2. And the reason is that if I went down to d is 1, I would have another factor of n to the 1 over d, whereas these are only differing, these are both sort of poly-logarithmic, right? And so when we put this together, we get upper bounds on the statistical dimension. The lower bounds are not too tricky to obtain either. I'll give a related argument in a moment. So up to some constant that depends on d, this is like n to the 1 minus 2 over d, and again on the lower bound, n to the 1 minus 2 over d. Okay. Actually, it turns out you can do a little bit better on the lower bound in 2 dimensions. You can get a log squared factor in here. Okay, so if we put all this together, we get the following worst case upper bound. So it says that the risk is bounded above by up to poly-logarithmic factors, and in this talk I'm not going to worry too much about the poly-logarithmic factors, just focus on the dominant terms in n, and we're bounded above by n to the minus 1 over d. Okay? And interestingly, this actually is matched by a minimax lower bound of the same rate, same order. Okay, so this is here where I'm taking an infimum over all estimators. So in terms of how you obtain the lower bound, the key observation is a sort of geometric one, or a combinatorial one, which is one of the reasons why I chose to present this here. So if I look at the lattice, what I can identify is a large anti-chain in this lattice. So let's suppose I have the set of vectors in the lattice whose sum is n1. Okay? So it's a well-known combinatorial problem of how many such vectors there are. That's what's being illustrated by this hyperplane here. The point is that none of the vertices that are illustrated by orange dots are comparable to each other in this ordering. Okay? So this is an anti-chain as a set of mutually incomparable vertices. And so none of these points all of these points are mutually incomparable. And I claim that it's a large anti-chain. How many such vectors are there? Well, you initially think that it should be n1 plus d minus 1, choose d minus 1, right? Because this is a well-known combinatorial problem. Actually, because these have got to be positive numbers and not just non-negative ones, you lose the d1 and you just have n minus 1 choose d minus 1, and that's at least as big as n1 minus 1 over d minus 1 to the power d minus 1, which is at least n to the, what do I want to say here? 1 minus 1 over d, right? Yes, okay, good. Okay, and the fact that you've got a lot of such vectors allows you to construct, to think about a whole set of distributions that are indexed by the vertices, or indexed by 0, 1 to the w, and then you can apply Asward's lemma, and that's what gives you this minimax lower bound. So it's interesting that even though we thought we were doing a sort of dumb argument by deleting these edges here to give us bounds on the statistical dimension, this turns out to be essentially sharp up to these poly-logarithmic factors, and that translates into matching upper and lower bounds for the worst case risk. Yep.
In your graphic with the orange dots, do you only have that one anti-chain, or do you have others kind of emanating from other vertices?
You would have other sets of mutually incomparable vertices, but you see what you can do here is I can think of all vectors that are 0 below this diagonal and 1 above the diagonal, and then I'm completely free to choose anything between -1 and 1 on each one of the sets in orange. But if I considered another anti-chain simultaneously, I wouldn't have the same freedom to do that, because there would be relationships between the vertices in the different anti-chains. Yeah. Okay, so now there's actually turns out to be an extremely interesting story. It's been well known for a long time that the right rate of convergence in one dimension is order n to the minus 2/3 with no logarithmic factors. If you look at the work of Chatterjee, Gunter, and Sen, that gives us a rate of n to the minus 1/2 in the two-dimensional case. But then we get this sort of elbow in the rates, and in the higher dimensions, it's n to the minus 1 over d. Actually, they're equal when d is 2, because n to the minus 2 over 2 plus 2 is equal to n to the minus 1 over 2, right? But there's a sort of phase transition in the rates, and you can explain this by reference to sort of two competing factors. In the one-dimensional case, there's a strong analogy between isotonic functions, monotone functions, and functions with one bounded derivative. This was alluded to in Bodhi's talk. And you get the same rate of convergence as you would if you were estimating a bounded Lipschitz function. But in the higher dimensions, it's not the smoothness that's driving the rate, it's this geometrical quantity, the anti-chain, that's driving the rate. Okay? And there's something very interesting about this from a theoretical point of view. There has been a kind of folklore theorem in the literature that says that you shouldn't use global empirical risk minimizers when the bracketing entropy integral diverges. And it's diverging quite rapidly as soon as it behaves like this, because you've got to integrate the square root of this guy. Okay? So this emanates from work of Biaget and Massart, where they looked at Hulda smoothness classes, and they showed that exactly at the point where this entropy integral diverges is where the MLE, or the global empirical risk minimizer, ceases to be rate optimal. Okay? But that example has sort of been extrapolated rather too far, it now appears, to say you shouldn't use global empirical risk minimizers when the bracketing entropy integral diverges, certainly if it diverges this quickly. And what we're seeing here is that this is an example where the bracketing entropy integral does diverge rapidly, and yet still we're attaining the minimax optimal rate. So I think if there are sort of theoretically minded people here, it would be very interesting to know when one could expect global empirical risk minimizers to still attain minimax optimal rates in settings where the entropy diverges, because we now have examples of both cases. Right? I think this is the first example we know of where such a phenomenon occurs. Okay, let me move on now from sort of worst case analysis to talk about oracle inequalities or sharp oracle inequalities. So the motivation here is to think that there should be some types of signal vector that we can estimate particularly well. Now, if you think about the least squares estimator, it's going to be piecewise constant, and so you might hope that if the true signal was itself piecewise constant with not too many pieces, then you might get a faster rate of convergence than the worst case rate. Okay? So if we let mk of LDN be the collection of monotone vectors on the lattice for which you can partition the lattice into hyperrectangles on which the restriction of theta to each hyperrectangle is constant. Okay? Then what we can say, this sharp oracle inequality, is that for any signal vector, it doesn't have to be monotone, the risk is bounded above by some infimums but then a sum of two terms. This term is a sort of approximation error term. It's how well can this particular theta that's k piecewise constant approximates the true signal vector. And then there's an estimation error term here as well that depends upon the choice of k. Okay? So as k increases, this approximation error term is going to decrease, but this estimation term is going to increase. Okay? But in the best case, let's imagine that my true signal were itself constant. Then this approximation error term I could get to vanish, and the estimation error term is going to be like n to the minus 2 over d. So instead of being n to the minus 1 over d as it was in the worst case, we've now got n to the minus 2 over d, a faster rate of convergence. This is an adaptation result. It's called a sharp oracle inequality because the leading constant in front of this approximation error term is 1. Okay, I couldn't hope for it to be better than that. And moreover, what's interesting and that's a consequence of this, or very related to this lower bound of log squared n when d is 2, is that you cannot improve this adaptation rate for the least squares estimator. So in the worst case situation, we were looking at a minimax lower bound. This is a lower bound of a different flavor. It's a lower bound for the performance of just the least squares estimator and just for one particular function, the 0 function. I could take any constant function. It wouldn't matter at all. But this rate is n to the minus 2 over d and when d is greater than or equal to 3, and I can improve that a little bit when d is 2 because I can actually force a logarithmic power in here as well. So let's go look at a corresponding picture. In up to 2 dimensions, it's known that you can get a parametric rate of adaptation. Okay, that's the best thing that you could hope for. But what we're seeing is that we get this rate of n to the minus 2 over d. This is in the nicest setting where I'm just estimating a constant function. Okay, but that is not the parametric rate. It's still, even if I were in d dimensions, if I told you that the true signal is constant, you'd just estimate it by the mean of the observations, and you would get a parametric rate in arbitrary dimensions. Okay, so what we are seeing is we're seeing that the least squares estimator, from a worst case perspective, is minimax optimal up to these logarithmic factors. In terms of adaptation, it does adapt, it does get a faster rate, but it doesn't adapt at the parametric rate. So it would be an open problem as to whether you could find another estimator, because it's not just our theory here. We've got lower bounds for the least squares estimator that tell us essentially we can't improve it, but maybe there's another estimator that does achieve the worst case risk over the whole large set and also attains this parametric rate over the smaller sets. It's unknown whether such an estimator exists. Okay, just before I finish with fixed design, so an extension of this problem is to think about the setting where your covariates take values in more general domains. Something like that, okay? you can still think about a monotone lattice intersected with this domain. Actually, we can extend our results in a certain sense. We need to think about the smallest enclosing cube. So, okay, and the largest enclosed cube. No, that's not good. Let's pretend it's like that, okay? So let's say that this has got side length r and this has got side length little r. You could think of capital R over little r as something like a condition number, okay? And if you call kappa that condition number, our results extend to the setting where you're willing to think of kappa as being a constant. Okay? You just have constants that depend upon kappa now. Now what's interesting about that is that if you look at recent results, for instance, by Han and Wellner in the convex regression setting, what they find is that the behavior of the boundary of the domain plays a crucial role in determining the rate of convergence. So whether it's smooth, in which case you kind of get a worst case rate, or whether it's polygonal, with a relatively small number of vertices, that really affects the rate that you get. But in the isotonic regression setting, it seems that we're somewhat less sensitive to the behavior of the boundary of the domain, and provided we're willing just to think of this condition number as being like a constant, then we're okay, all our results go through. Okay. Let me say a little bit about random design. The basic message for random design is the results are similar, the proofs are much harder. For simplicity, let me just think about the case where the covariates are uniformly distributed on the domain. I could certainly extend this to the setting where the true distribution had a Lebesgue density that's bounded above away from infinity and bounded below away from 0. But let me not worry about that for now. Just think about a uniform distribution. In this random design setting, there are two loss functions you might consider. The first is the one that we've already thinking about, the expected loss on the observations, although now I have to take the expectation over those observations as well. But also I might think about this population L2 loss as well, which is perhaps a more natural loss in this setting. Okay, and the results say that in terms of worst case risk, we've got the same upper bound for both types of loss, both types of risk, with a slightly larger poly-logarithmic exponent here. And then we also have similar sorts of sharp oracle inequalities, or at least it's sharp in the case of the Rn loss, because we can take C to be 1. In general, I need a kind of universal constant here as well. So in terms of the technical challenges here, if I were to look at the entropy of the natural class of functions, which is the intersection of the class of block increasing functions with the set of functions whose infinity norm is at most 1, then its L2 entropy is like epsilon to minus 2 into d minus 1. And if I were to just use a standard chaining argument, I would get a suboptimal risk here. Okay. So what we did in the fixed design case was we decomposed our lattice by deleting edges, or deleting constraints, and then we were able to decompose it into lower dimensional problems, but we don't have this geometrical structure in the random design setting. Okay. So a little bit like I was doing on the board over there earlier, but using a basic inequality and a peeling argument, we get down to trying to control some sort of empirical process like this. And the analog of removing the constraints here is to divide the problem into layers, okay, in one of the dimensions. We've got good control about how many points are going to appear in each of the layers. And then, crucially, we can use the decreasing nature of the function or increasing nature of the function to bound the envelope function within the ELF layer in a way that improves with L. Okay, and that's what allows us to control the contribution to each slice by a chaining argument. Okay, so it's a very quick sketch of how the proof goes. It's a lot of work to get it all done. Okay, and in terms of the lower bound, well, it's again a similar sort of story. For both risks, we have a worst case, a minimax lower bound of n to the minus 1 over d, and for the least squares estimator, we can't do better at the origin or for any fixed constant function than a rate of n to the minus 2 over d. So there's an interesting connection here with the Erdős-Zakaria theorem. So this is in the case where d is 2. And you want to know something about how big a chain or anti-chain do you have in the two-dimensional case. So you've got you can think of one variable being ordered without loss of generality, and then the other variable is going to be a uniform permutation of 1 up to n, okay, in terms of its ordering. So the Erdős-Zakaria theorem says that amongst any set of r minus 1 times s minus 1 plus 1 observations, you have to have either an increasing subsequence of length r or a decreasing subsequence of length s. Okay? So that's what tells me that I have to either have a chain or an anti-chain of length at least n to the half. Okay? And so that explains something of where this lower bound comes from in the two-dimensional case. Okay, so let me wrap up. Isotonic regression does behave quite differently. Let's say between d is 1 and d is greater than or equal to 3, with d is 2 as being some sort of transitional case. We saw that the least squares estimator does achieve the minimax optimal rate if we're not considering poly-logarithmic factors, even though when d is greater than or equal to 3, the entropy integral diverges rapidly. And I think this is the first instance where a global empirical risk minimizer does achieve this minimax optimal rate in such circumstances. It also adapts to signals that are piecewise constant with not too many pieces, but it doesn't do so at the parametric rate. It does so at a strictly non-parametric rate, and that's not just a consequence of our bounds, that is a property of the estimator. And the results, by and large, go through, although the proofs are more complicated in the random design setting. So the paper, if you're interested for more details, is available on the archive. And I will stop there. Thank you very much.
We have time for some questions.
Rebecca.
With your kidney bean shape over there, you said, well, we're going to look at the intersection of it with the 2D lattice. And I wondered why that's the natural thing to do as opposed to assuming that you somehow have a smooth warping of the lattice.
Not the 2D lattice, this would be a d-dimensional lattice.
Well, okay, yeah.
Yeah. So I'm imagining that I've got my design points. Oh, this is difficult to draw. You know, look something like that. Right, this is where I observe my y's.
Oh, I see what you're saying now. Okay, yeah.
Yeah.
Thanks.
Any other comments or questions for Richard? If not,
Richard?
Yeah.
Can you comment on, you have this block increasing design, can you comment on the connection to the change point problems?
How would you like me to comment on the change point problems?
Whatever you like.
Okay, so in the one-dimensional case, there's been some rather recent work by Chao Gao and Chenhui Zhong and a co-author whose name temporarily escapes me, that says in terms of the lower bound on the risk, if you know that you're increasing, and you, oh no, hang on a minute, sorry, let me rewind a moment. If you've just got one change, then you need to have a factor of log n or log n over, yeah, log n in the lower bound. So that's closely related to the change point problem, right? Yeah, I don't know to what extent those results extend to high dimensional settings, though. I think that's all about all I can say in relation to the change point problem.
You mentioned other problems, convex restrictions. Can you make a comment whether this is similar, very different? What's?
It certainly seems that one big difference is that the shape of the boundary matters a lot more in convex regression. It's like the least squares estimator has even more dramatically bad behavior near the boundary than it does in the isotonic case. And so I was quite interested to see that the shape of the boundary doesn't play such a big role in the isotonic case. In both cases, you can think about it as projections onto a convex cone. So there are some similarities in the problems, but there would also need to be some differences in the analysis as well.
When you increase the dimension, doesn't it become sort of very restrictive to have it sort of isotonic in every single dimension? Wouldn't it be okay to relax it a bit in some of them?
Well, I mean, you could say that, but you could say the fact that we're getting this cursor dimensionality rate, n to the minus 1 over d, is telling me something about how many functions that there are that are like that. So you could make that argument in both directions, I think.
Could you try to kind of mix the problem, say some coordinates are unrestricted and others are, and then I could play a little bit with how this enters into the...
Yeah, I think there are a lot of interesting problems that would involve mixed sorts of constraints. I've looked at additive models where you can have, say, one component being increasing, another one being convex, another one being concave and decreasing. Yeah. Axel, go on.
Isn't it? Actually, I feel a little bit more the other way around. So that means it is more, at first glance, kind of surprising that if you have so much structure, like monotonicity in each coordinate, that essentially you get curves of dimensionality, rates of convergence. And isn't it more the situation that the minimax perspective is here really a very pessimistic one in a sense? I mean, this is a lot of structure, right? You have monotonicity in each argument. And
but even the best case you could possibly hope for is a constant.
Yeah. So I understand that. This is what you showed in the talk, actually. So is there kind of, could you think in terms of adding, let's say, a little extra structure so that you somehow really get maybe rates which just scale logarithmically with the dimension, or something better?
Yeah, I mean, and the most obvious structure is an additive structure to me.
But in 1D essentially. So
exactly, but and I think, but from the applications perspective, this has really been found not to be satisfactory, in particularly in these gene heritability studies.
Okay, if no more questions, let's thank Richard and then adjourn to afternoon tea.